Hello chemistry people, Amy here, coming to you today from school, obviously, so that if the sound's a bit different, that's why. Today I'm running a video on some of the definitions that we're going to need for topic 9.1, which is oxidation and reduction reactions. So I'm just going to pause and go over to my OneNote and then we'll start taking some notes. So as is my wont, we will start with the study guide. Now, my purpose with this video is not to cover all of this topic 9.1. I am just going to talk about oxidation and reduction as terms, what oxidizing and reducing agents are, and what we mean by variable oxidation numbers. I am not doing today talking about activity series or Winkler method. In terms of the applications and skills, we are going to be deducing oxidation states and naming transition metals, identifying and naming oxidized and reduced species and oxidizing and reducing agents. We're not going to balance half equations and we're not going to look at activity series. That will be our next video. We're not going to solve redox titrations and we're not going to talk about Winkler method. So these things here, we're going to need to keep in mind as we go through these points. So just those 6 points plus those guidance ideas. So let's start with the actual term redox itself. So redox is a word that's called a portmanteau. It is a sticking together of two different words. So reduction and oxidation. So a portmanteau like this is where you stick together two words because they belong together. So if you want to go back to a celebrity couple from when I first started teaching chemistry, something like Brangelina, it's that sort of idea. Okay. So in order to understand where these terms come from, it's probably easiest to go back to where they started, where we first started thinking about these types of reactions. Now, one of the first redox processes that was actually understood at any sort of quantifiable level was when we took iron ore, so iron oxide, and we heated it. And we formed iron and oxygen. So when we think about this reaction, we have solid iron oxide, solid iron, and gaseous oxygen. What this means over the course of this reaction, this is heavier and this is lighter. Now, in terms of conservation of mass, we know that it isn't actually lighter, but because this oxygen escapes, as I purify iron, it goes from being heavier to being lighter. So this is a reduction reaction. A while after that, and I can't remember whether it was Lavoisier or Priestley, worked out that it was oxygen that was being produced. So a reduction reaction was earlier defined as a loss of oxygen. So my iron oxide is losing oxygen to become iron, so it has been reduced. One of the other ways that we can talk about reduction is gaining hydrogen. Now, these definitions are super helpful for when we're talking about organic chemistry. So even though they're not the definitions that we will mostly be using in this chapter, you need to be aware of them, because the definition that we actually use, it's much harder to see in the same way we can see loss of oxygen or gain of hydrogen. The definition that we use most often in this chapter is that reduction reactions involve the gaining of electrons. So in that ion equation, I've just written, I effectively have iron 3 plus becoming iron with no charge on it, which means it has to have gained 3 electrons. Now, hang on, I can't just make electrons out of nothing. I'm a chemist, not a physicist. So where do I get those electrons from? Those electrons have to have come from the other thing in that reaction, which was the oxide ion. So my oxide ion, 2 of them are becoming an oxygen molecule. So I can't destroy electrons out of nothing. So I must have 4 electrons that are made, that are released. So my oxygen, so the opposite of reduction, and I talked about that earlier, the opposite of reduction is oxidation. So my oxide ion is undergoing oxidation because it is a loss of electrons. Oxidation can also be defined as, surprise, surprise, the gain of oxygen or the loss of hydrogen. And again, that is mostly useful in organic chem. So in order for a redox reaction like this to occur, I need a reduction reaction and an oxidation reaction occurring at the same time. That's why we call it redox. We can't have a reduction independent of an oxidation. The electrons that are given up by my oxidation reaction have to be absorbed by my reduction reaction. You can't have one without the other. So oxidation and reduction reactions happen all around us all the time. So these are the chemical reactions, because they're transferring around electrons, that are the basis for batteries, electrochemical cells, which we'll talk about later. They are the process by which we can use electricity to make chemicals. So for example, when you electrolyze water to make hydrogen, because we're talking about the movement of electrons, I can use that to generate electricity, or to use electricity in the case of an electrolytic cell. Okay. So let's look at another reaction and see if we can work out what is being oxidized and what is being reduced. So I have 3 magnesium solids reacting with nitrogen gas to form magnesium nitride. And that's a solid. Nitride, sorry, that is a solid. So this is maybe slightly less obvious than some of the others because I'm not dealing with hydrogen or oxygen. Think about what is happening. Let's start with my magnesium. I am starting with magnesium with a 0 charge. And think back to periodicity. What ion does magnesium form? I'll give you a second to pause and get your periodic tables. That's a second. It forms Mg2+, and because I can't create or destroy electrons, I have to have 2 electrons, there. On my other side, I have nitrogen atoms that have 0 charge, and they form 2 nitride ions. So again, look at your periodic table. So I have 2 nitride ions, which means I need 6 electrons over on this side to balance that charge. So which one is my oxidation and which one is my reduction? Oxidation is the loss of electrons. So this is my oxidation and this is my reduction. You always have to have one thing gaining electrons and one thing losing electrons. One mnemonic, one memory device that is often helpful to the students when we're looking at redox is oil rig. So oxidation is loss, reduction is gain. So this works. This is talking about electrons. It isn't talking about the hydrogen and oxygen. Oxidation is loss of electrons. Reduction is gain of electrons. And that ties into what we're going to look at later about electrochemical cells. But this is our key takeaway point for this video, that oxidation is the loss of electrons and reduction is the gain of electrons. So you might be able to see at this point, like keeping track of what my electrons are doing is really simple when I'm looking at stuff that is going to and from ions. So whether it's iron oxide becoming iron and oxygen, or whether it's magnesium and nitrogen becoming magnesium nitride, when I've got things that are clearly plus or minus charged. But that is not all chemicals. So there needs to be a way that I can keep track of how my electrons are moving within covalent compounds. So the analogy that I like most for this, I've stolen from, I think it's one of the crash course videos. Oxidation numbers are basically like in a divorce, who would get the kids being the electrons. So oxidation numbers, so ON, it's a way of assigning the number of electrons in a covalent bond. And there are a series of rules that allow us to do this. So, rule number 1, there is no talking about Fight Club. Okay, so rule number 1, if I have an element, the oxidation number is 0. So for example, in sulfur, that oxidation number is 0. In oxygen, it's 0. In, I don't know, magnesium metal, like we did before, it's 0. If I have what is called a simple ion, the oxidation number is equal to the charge. Oh, and one thing you're going to see. So magnesium 2 plus, the oxidation number is +2. We switch around the sign. So the sign is at the front on the oxidation number. That is something that the IB will mark against you for. So keep that in mind. For something like, I don't know, the nitride ion we talked about earlier, the oxidation number of that would be -3. Okay. Excuse me a moment. Okay, so my apologies. I just needed to double check something up here. So I have made the mistake that they indicate here. I have used the terms oxidation number and oxidation state interchangeably. So oxidation numbers are represented by Roman numerals. What I'm doing here is oxidation states because I'm using Arabic numerals. So let's go back and fix this. So this is oxidation state, and this has an oxidation state of 2 and an oxidation state of 3. This will become obvious when we start talking about the transition metals and the fact that that can have different oxidation numbers. So Rule 1 was talking about elements. Rule 2 was talking about simple ions. Rule 3 is when we start getting into molecules. So if it is an uncharged molecule. In an uncharged molecule, the sum, is that the way sigma goes? No, that doesn't look right. Yes? Sum of the oxidation states is going to equal 0. So, for example, in water, zero is going to equal 2 times the value assigned to hydrogen plus the value assigned to oxygen. Because water is an uncharged molecule. Okay, this will become more obvious when we do some practice, but we need a couple more steps. Number 4, if it's a charged molecule, which is also known as a molecular ion. So in a charged molecule, a molecular ion, the sum of the oxidation states is going to equal the charge on the ion. So for example, NH4 plus, it's going to be +1 is equal to nitrogen plus 4 times hydrogen. SO4 2 minus -2 is going to equal sulfur plus 4 times oxygen. So here's where we start getting into the stuff that has exceptions. So the usual oxidation state for the element is the same as the charge on its most common ion. Now, that's the way the textbook I've got in front of me says it. I go a slightly different path. Halogen, they are almost always going to have an oxidation state of -1. My exceptions are when you're looking at an interhalogen bond. So two halogens bonded together, or if you're looking at a halogen bonded to oxygen. Those are pretty much when you will see a halogen that is not a -1 charge. Oxygen, its oxidation state is almost always going to be -2, excluding when it's bonded to oxygen. Or fluorine. These exceptions come down to electronegativity. So thinking about the covalent bond between those things, which one is more likely to pull on those electrons and take them? So, oxygen, so hydrogen is going to have an oxidation state of +1, excluding what are called hydrides. Is that how I spell that? Yes. So in a hydride, it is the H- ion. Oh, where am I? Yes. Okay. So excluding hydrides where it's a H-1 ion, which would give it an oxidation state of -1. So oxygen, hydrogen, halogens. Then you've basically got your alkali metals are going to be +1, and your alkali earth metals are going to be +2. Everything else, carbon, nitrogen, all of our transition elements, they will vary depending on what they're bonded to. So the ones that are going to be most useful for you to just outright memorize are the oxygen and the hydrogen. Halogens are generally pretty obvious, but these exceptions here can get a bit tricky. So let's actually practice it. Let's look at these guys I did earlier. So let's look at NH4+ and work out the oxidation states of the elements in that. So NH4+. So overall, +1 has to equal nitrogen plus 4 times hydrogen. By definition, by convention, my hydrogen is a +1. And then, like grade 7 algebra, the nitrogen would have an oxidation state of -3. Let's look at the sulfate ion, so SO4 2-. So -2 is going to equal sulfur plus 4 times oxygen. So my oxygen is, by convention, unless it isn't bonded to other oxygens and it isn't it doesn't have a halogen attached to it, a fluorine more specifically, I have 4 times -2, which gives us -8. So sulfur is going to have a +6 oxidation state in this compound. Let's do another compound for each of these guys to show you that my oxidation states can change. So let's do a different nitrogen compound. So obviously I could just do nitrogen gas, but let's pick something a bit more complex that we can actually work out. So if I have NO3-, this is the nitrate ion. So it has an overall oxidation state of -1. So -1 is equal to nitrogen plus 3 times oxygen. So 3 times -2 is -6. So nitrogen here is a +5. Let's do another sulfur. Let's do hydrogen sulfide, which is rotten egg gas. So overall, this has a charge of 0. And it is 2 times hydrogen plus sulfur. So 0 is equal to 2 times 1 is 2. Shocking. Plus sulfur. So sulfur has an oxidation state here of -2. So we can see that the elements can have variable oxidation states depending on what they're attached to. Let's now talk about using these same principles. Let's talk about how we apply that to discussing oxidation numbers for transition metals. So let's go over here. So let's look at some transition metals. Now, one of the characteristics of transition metals is that they have quote unquote variable oxidation numbers. And note the change in language. I've gone from talking about oxidation states to talking about oxidation numbers. So when I talk about the oxidation states of transition metals, where I can express those in Roman numerals. And what that can then be done is we can differentiate between them. So let's look at manganese. Manganese is fun. So MnO2 is a solid versus the manganate ion, MnO4- aqueous. Now, MnO4 aqueous and MnO4- aqueous is this gorgeous, like purplish color. It's really gorgeous, but it's one of those colors that you look at and you think, damn, that's going to be toxic. And what do you know? It is. So let's look at the oxidation states of these two guys. So let's try and work out the oxidation state of manganese in each of these. So overall, this molecule has a charge of 0. So that's going to be manganese plus 2 times oxygen. So 0 is going to be equal to manganese. 2 times -2 is -4. So manganese here is going to have an oxidation state of +4. How I change that to manganese's oxidation number. So this is manganese IV oxide versus, let's look at this guy. So this is going to be, the overall charge is -1 plus manganese plus 4 times oxygen. So -1 is manganese, 4 times -2 is -8. So this has an oxidation state of Mn plus 7. So this is called the manganate 7 ion. Cool. So these guys, and it's a little bit confusing, but these guys that are numbers, these are the oxidation states. These guys here that are the numerals, those are the numbers. Okay. So let's go back and look at our study guide so I can make sure that I'm covering. So I've talked about oxidation and reaction in terms of oxygen and hydrogen gain and loss, electron transfer and change in oxidation number. Yes. I've talked about variable oxidation states. I've talked about how we deduce that. I've talked about how we deduce the name of a transition metal. Let's talk about oxidizing and reducing agents in redox reactions. So let me just mark off some space for us, and I will talk about oxidizing and reducing agents. Agents. All righty, so let's look at what's an oxidation reaction? What's a redox reaction? Let's talk about one of the reaction in one of the electrochemical cells we're going to look at in the second part of this topic. It's where I react copper 2+ ion with solid zinc, and I form solid copper and zinc 2+ aqueous. Okay, so let's split this into two half reactions. So I clearly have copper 2+ becoming copper. How does it do that? It does it by gaining electrons. I then have zinc becoming zinc 2+. How does it do that? It does it by losing 2 electrons. So let's define our oxidation and reduction reactions. So oxidation is the loss of reaction, so oil. So this is my oxidation. Reduction is the gain. So this is my reduction reaction. So, sorry, oxidation and reduction refer to the reaction. But let's talk about this in terms of what causes oxidation or reduction. So, copper, let's think about it slightly more violently. Copper is ripping electrons away. This copper 2+ is ripping electrons off stuff. So, this is going to cause electron loss in something else. So if something is a cleaning agent, it doesn't itself clean. It causes cleaning on another object. So my copper 2+ is causing electron loss somewhere else. Electron loss is oxidation. So My copper 2 plus is causing electron loss, causing oxidation in something else. So what that means is that it is therefore an oxidizing agent. Okay. My zinc, and hopefully you see where I'm going with this. Let me find, that should stand out enough, hopefully. My zinc is pushing its electrons off. So my zinc metal is causing electron gain in something else. Electron gain is reduction. So we would call zinc, therefore we would call that the reducing agent. Because it is causing reduction somewhere else. So let's look back at, have I? Let's go through another reaction and talk about it. Actually, let's go back to the magnesium nitride experiment. Let's go look back at the magnesium nitride reaction that we looked at earlier. So we had 3 magnesium metals reacting with a nitrogen gas molecule and forming magnesium nitride solid. So let's work out in terms of oxidation states what is happening. So elements have oxidation states of 0. This is now the magnesium ion, so it is now a +2, and this is the nitride ion, so it is a -3. So nitrogen, what reaction has nitrogen undergone? It has undergone, sorry, my nose is itchy. Nitrogen has undergone a reduction reaction because it has decreased in that oxidation state. What that means, though, in terms of how my electrons are moving between these two, is it has ripped electrons off. It has removed, it has caused electron loss. If it causes electron loss, it is by definition an oxidizing agent. Because it is causing electron loss in something else. Okay, now let's confirm by looking at the magnesium. So magnesium has undergone an oxidation reaction. Because it has effectively lost electrons. So because its oxidation state has increased. It's gone from 0 to +2, so its oxidation state has increased. So it has caused electron gain, which is what we call a reducing agent. Okay, let me go up and double check how we're doing against our study guide. So we have talked about what oxidizing and reducing agents do. We've talked about species oxidized and reduced and how that links to reducing and oxidizing agents. And I've talked about these. Fantastic. So thank you so much. Our next video is going to discuss the different reactions, some of the different redox reactions, and we will be doing some experiments in class that look at this as well. Thank you so much. Have a fantastic rest of your day, and I shall see you next time. Bye.